Finally, we got only last case. What's the last case? You have two solutions. The last case is G1 less than 0, G2 less than 0. That's all good. Then the beta 1 is not 0, beta 2 is not 0. We don't care about the beta. So among the two solutions, this does not work. You cannot be negative. So that's the only solution. X equal x1 equal 0.82, x2 is 9.91, and the b1 equal this, b2 equal this. See, that's negative, that's negative. It's good. And what's your solution? This is your solution. The f equals negative 0.7443. So finally, you get your solution by just, we call it brute force. You look at all the four cases, and basically, you brute force it. All right, and there's a simple strategy. You look back into this graphic solution, and there's another surprise. Your solution is right at this point. Can you see it? And then x equal 0.7 something, 8, and the y equal 0.8. This is negative 0.744. Is that right at this corner point? And the lower, the better. Okay, here's go. Here it is. Anyway, you got the idea. It's a lot of computation. Even a simple question, do it by hand, it will take you a little while, probably 30 minutes if you're very good. Anyway, let me see the time. Okay, I got a good amount of time. After this, we're going to look for all the MATLAB command. But before we move on, I want to summarize what we did so far, and especially the analytic method. We learned that the canonical form, you have the design variable x1, x2, the objective function. Wait a moment. How about if I say maximize this function f x1, x2 equal x1 times x2? Well, you say I have not learned it. Of course you learned it. If anything maximize, all you need is to put a negative. If you put a negative, you minimize it, then remove the negative, you maximize it, right? Right? So that's an easy problem. You always can change into minimize, and that's nothing magic. Another way we can think is so-called the dual problem. Sometimes you can exchange the constraint and the objective function. Let me give you an example. If the manager say, I have this much amount of dollars, I want to maximize my profit. So you can say, I have the constraint of my capital. I want to maximize the profit based on the capital. The same question can turn around, say, I want to use make $1 of profit to minimize the cost. You know, maximize the profit means you want to make $1 of the profit, minimize the cost. The same question. That's called the dual problem. Well, you can read the textbook later on if you have interest. So there's a lot of reference for that. So you can always change things into minimize. Second, you have in equations. That's nothing new. You just need to add slack variables. And when you add this slack variables, a pitfall is here. You need to make sure this is positive. Then you move the equivalent without that is less or equal. But if how about it's greater or equal, then you're going to minus a z1 square, right? That is we call it, used to call it surplus variable. And that you cannot make a mistake. So since it's less than equal, then you add a positive number, a non-negative number. But if it's greater than equal, then you minus a non-negative number. That you need to keep in mind. Otherwise, you get all garbage. And then, second, the Lagrange method could rewrite into this way. You build a new objective function. In that objective function, and you have the original objective and add this two constraint also be the objective with the Lagrange multiply beta 1, Lagrange multiply beta 2. So to get those 6 equations is nothing new. That's what you learned in the second lesson. That's the Lagrange method. The only thing maybe look differently, you can write this into the other side. That's the only difference. So after you get all these 6 equations and the 6 variables, there's no magic. All left over is algebra. Then you look at so-called solution space. And your solution space is very limited. It's a few points. And this is highly nonlinear. You get from here, you get a whole list of points. How many we have? 1, 2, 4, 5, 6, 7, 6, 8. We got 8 different points. So among the 8 points, you check one by one. Check what? You check if satisfy all the constraint equation, satisfy if it is good for all the inequation, then automatically eliminated the 7 points. The only points left is this point. And then that's the solution. And you see it from the graph here. The solution is right here. It's on the boundary here. Look at the contour. Move which direction? The further you move out, the more negative. Can you see it? And then means the more you shift this contour curve out, the better off your solution is. But you cannot move out of the physical, the feasible. I always have the trouble. The physical, feasible domain. And where's the domain? By the 2 constraints, you have to be inside of this ellipse. Also have to be inside of this triangle line, and then your feasible domain is made by these 4 lines. Here and here. And along this 4 line inside, this one is the best. And this point gives you the optimal solution.